So, to summarize, you have a choice of how you want to write your zeta, but did I say zeta? I meant lambda, plus or minus. So that is lambda. Now, I won't take too long to explain a lot of things. I'll summarize. Now, if a system is such that this, what is inside the bracket, is bigger than 1, that's an overdamped system. Are we together? Now, in an overdamped system, so we are saying, we can say C squared is bigger than 4 km from there. Or if we want to specify from here, you can say zeta is greater than 1. Then the system is overdamped. And when the system is overdamped, remember, we propose the system like that. Okay? So if that's our displacement, then we are simply going to say x is equal to e to the power, you can use that, or if you want that, which is equal to, now because there are two of them, we have this plus this as the first solution. Then this minus that is the second solution. Now because there are two like that, we are going to say A, e to the power, the one with plus B, e to the power, the one with minus. I'm not simplifying the bracket. It's simply all that, or all that. Can you see that? So it's all that and all that added together. As you can see, this is an expression e to the power this, e to the power that. We characterized e to the power this, e to the power that, and we said it's like this. Remember? So, because of the minus, effect of minus is to change direction so that instead of going this way, it will be going that way. That's the resultant curve when we have an expression like this. Because we have two terms, each of them like that, so they add up to give us another curve, but also like that. Is this thing vibrating?
No.
It's not. Why are you saying no?
It doesn't cross the equilibrium position, so there's no up and down.
I like the first part. You say it doesn't cross.
Yes, let me put simple terms here.
If you say it doesn't cross, it's not very correct. Because I could play with you and I could do this. Is it vibrating? Now it has crossed.
Oh yeah, you're right.
Is it vibrating?
No, it's not oscillating. Yeah.
It's not oscillating. So the crossing the point is not. That's not the fact. The fact is it's not oscillating. Even if it crossed the line, it's not oscillating. Are we together? It's simply settling, and that's how you design your damper. If you are designing a damper, you can use a spring to behave as a damper this way. Can you see that? When it goes over a bump, if it's a car, when it's settling, what does it do? It doesn't do this. It goes shh. So that's damping. No, I'm saying damper. I want to say shock absorber. You can design it that way. You put this in a car. Every time it goes over a bump, when it's coming back, what does it do? It doesn't do this. It just goes shh, and you continue going. So you can design your shock like this. Are we together? It doesn't vibrate. Right. Let's look at the second one. The second one is when this is equal to that. Okay? When this is equal to that, what happens? This whole thing disappears. And we say the system is critically damped. Sorry, I'm taking shortcuts. I'm not even writing, I'm talking. Because time is short. So, if we have something like that, we have two real roots, which means lambda 1 is equal to this plus 0, which is that. Lambda 2 is this minus 0, which is again that. Or if you want, you're using this one, then it's this. So you